Welcome back, Math 30-1. Today's lesson is just a continuation of yesterday's lesson, which is trigonomic identities. So in this lesson, we're going to know more on what are our restrictions and how to use trigonomic identities to prove more complicated trigonometry equations. So just to start off, what is a non-permissible value? Because that becomes very important with these. A non-permissible value is when we're pretty much dividing by zero. When we have a trigonomic identity, especially in tangent, cotangent, secant, cosecant, these all will have non-permissible values because we're going to get something over sine or cosine, which is, in a certain case there, our denominator can't equal 0. So for instance, tan is equal to sine x over cosine x. Well, in this case, cosine x cannot be equal to 0. Just like secant is the same as 1 over cosine x, which in this case cannot equal to 0 because we can never divide by 0. Since we divide by 0, we have a non-permissible value. Now if I look at cotangent x, we have sine x as the denominator, and same with cosecant x, we have sine x as the denominator, and sine x cannot equal to 0 because as soon as we divide by 0, it is a non-permissible value. So that's how we find our non-permissible values. Now, we're also going to need some hints here on how to solve more complicated trigonomic identity questions. So the first thing we should always do is begin with the more complicated side and try and make it less complicated. If possible, we're going to use our reciprocal, quotient, or Pythagorean theorem identities. For example, the Pythagorean theorem identities is excellent anytime a trigonomic functions are involved. So when we're squaring trigonomic functions, we use the Pythagorean. Okay? Another thing here is, if necessary, change all trigonomic ratios to sines and or cosines. So if I have tan, make it sine and cosine. Okay? So we want everything in sine and cosine instead of tan and cotangent. And also, we'd rather have sine and cosine instead of secant and cosecant. Now the fourth thing is look for factoring as a step in trying to prove the identity. So once we're there, then look for any factors we could take out. And then number 5 is, if there is a sum or a difference of fractions, combine to make a single fraction. So we want to combine to make single fractions. So here we're going to look at some examples. So classroom example number 1, it says consider the statement 1 over cos x minus cos x is equal to sine x tan x. So first it wants us to verify the statement for pi over 3. So I'm going to have 1 over cos pi over 3 subtract cos pi over 3 is my left hand side, and my right hand side is just going to be sine pi over 3 multiplied by tangent pi over 3. Now if we remember, pi over 3 is the same as 60 degrees, and that's when my sine is going to be long, 3 over 2, and my cos is only going to be 1 over 2. So this here is going to be 1 over 2, subtract 1 over 2. Okay? So that's the same thing as 2 subtract 1 over 2, which is the same as 3 over 2. Now, we want sine, pi over 3 is my big one, so that's root 3 over 2. And then we have to multiply it by tan. Tan is x over y. Y over x because of Sir Coxeter-Tix. So that's going to be my y, which is root 3 over 2, divided by 1 over 2, will just give me root 3. I multiply these together, and I'm going to get 3 over 2. And these kind of prove each other. Okay? Or in this case, it doesn't prove each other, but it verifies it that it works in this situation. Now, we want to use a graphing calculator to show that this statement is true. So what I would do then is I would just plug this part here into y1 and this part here into y2. And we should get two equal graphs, or it might look like one single graph. That means that this identity is true, that this side probably does equal to that side. Now we are going to prove this statement using an algebraic approach. So remember what it said here. We want to do step 1, look at the more complicated side. So for me, I think this is the more complicated side, so I'm going to look at that side first. So I'm going to go 1 over cos x minus cosine x. Okay? And that's equal to, we have sine x, tan x. So that's going to be sine x multiplied by tangent of x. Okay? Now, I look at this here. In order to combine these, what do I need to do? I need common denominators. So this is going to be 1 over cos x, subtract cosine squared x all over cos x. All I did was multiply this by cos x over cos x to get this part here. Now I can add this together. I'm going to get 1 minus cosine squared of x all over cos x. Okay? Now I look at this here, and I'm going to look at my identity sheet. This looks like one of the Pythagorean ones because we have a squared, so there's probably a Pythagorean identity here, and I have 1 minus cosine x. So if I look at that here, if I go 1 and I move cosine x to this side, I'm going to end up getting sine squared. So this is equivalent to sine squared x all over cos x. Okay? Now I'm going to look at this side here, and we're going to remember it says one of our steps is to make sure everything's in sine and cosine. So this is going to be the same as sine x multiplied by sine x all over cosine x. Because tangent is Sir-Coxeter-Tix, which is y over x, and that's going to be sine x over cosine x. Because that's also our quotient, or our division one right here. Okay? Now I look at this. This is going to give me sine squared x all over cosine x. And these here are equal. Good. Now it wants us to state the restrictions in terms of x. So I look at this. We have a denominator here, so we know my denominator is cosine x. So I have cosine of x cannot equal to 0. So I look at this, make my little box, and when cosine is 0, that means there's no x value. That's going to be at my y-axis, so there and there. So every time that this is going to be pi over 2 and 3 pi over 2. Then back to more. So every time we have x cannot equal to pi over 2, and we're going to go plus and pi. Okay? Because in other words, we're looking at tan here, and the period of tan we know is n pi, and we know n is an element of integers. So this is the answer for that one. Okay. So now let's take a look at class example number 2. It says prove this following identity here. So, and then determine the non-permissible value. So I'm going to first look at left-hand side, which is the same as sine x cosine x squared plus sine cubed x is equal to 1 over cosecant x. So we want everything here in terms of sine and cosine. So I'm just going to go, this here is the same as 1 over sine x, which is the same as sine x. Okay, so this side's done. It's as simplified as possible. Now I'm going to simplify my complicated side, which I probably should have done first. So first I'm going to look at what can I factor out of everything here. I could factor sine x out of both of those. So this is the same as sine x multiplied by cos squared x plus sine squared x. Now, what is the value of this? The value of that is going to be just 1, because cos squared x plus sine squared x is one of my Pythagorean identities, and we have that right there, and that's equal to 1. So I have just sine x here. And now we look at this. This is true. Now I want to find out what are my non-permissible values. So in this case here, we know that CSC of x cannot equal to 0. Okay? So in other words, we have 1 over sine x cannot equal to 0. And there's no way this can be equal to 0, but we have sine x cannot equal to 0. Okay? So sine x cannot equal to 0. So I'll draw my quick thing there. So when is sine x 0? That's going to be at 0 and pi, and then we go back to 2 pi. So this one here is always going to be just, we're going to have at n pi. So x cannot equal to n pi, where n is an element of all integers. Okay? So class example number 3 states, consider the identity sine a over tan a all divided, sine a plus tan a all divided by 1 plus cos a is equal to 1 over cotangent of a. So prove the identity algebraically. So I'm going to first look at this side here because this is going to be my complicated side. Okay? So this is my tricky side here. So I'm going to look at the tricky one first. So I have sine a plus, well, tangent, I'm going to put this into forms of sine and cosine. So I'm going to have sine a all over cos a. Okay? And that's going to be all over 1 plus cos a. Now, I want to simplify this a little bit more. In order to add these together, I need common denominators. So that's going to be cos a sine a, cosine a, sine a, all divided by cosine a, because we need a common denominator of cosine a, all plus sine a, all over cosine a. And this is all over 1 plus cosine of a. Now I'm going to continue this here, and we end up getting cosine a sine a plus sine a all over cosine a all over 1 plus cosine a. Okay? Now, looking at this, I'm going to rearrange this as a multiplication statement because this is over 1. So I'm going to have cos a sine a plus sine a all over cos a. And then we want to multiply this by 1 all over cos a plus 1. Okay? Oh, right there. There we go. So I look at this here. I could factor out of this a sine a. So I'm going to be equal to, we're going to have sine a multiplied by cos a plus 1 all over cosine of a, and this is multiplied by 1 over cos a plus 1. Now these here cancel off nicely, so I'm left with sine a over cos a. Now sine a over cos a is the same thing as tangent of a, which is the same thing as, if we look at our identities, 1 over cotangent of a. So now these do work and it proves. So we got this side to equal to my other side. Now, what are the non-permissible values of the identity? So I want to figure out what my non-permissible values are. So first, I'm going to look at this side here. So I'm going to look at my left-hand side. So I know that 1 plus cosine of a cannot equal to 0. Okay? So in other words, I have cosine of a cannot equal to negative 1. So I'm going to take a little look at that here. Where are these values on this? Negative 1 for a is only going to be at pi. Okay? So we have, in this case here, we're going to have x, a cannot equal to, every time we have pi there, so that's my negative 1 for a, so that's going to be pi plus 2, or 2 and pi. Okay? Now let's take a look at my other one here. I have tan. Well, if we're looking at tan, tan is the same as sine over cos. So also know that cos a cannot equal to 0. Okay, so where's cos a not equal to 0? Here and here. So it's at pi over 3. So a cannot equal to, pi over 2 plus n pi. Okay, for the tan. Now if we look at my right-hand side, I know that cotangent cannot equal to 0 as well. And we know cotangent is the same as this here, so we have sine A cannot equal to 0 and cos A cannot equal to 0, but we already did cos A cannot equal to 0 here, so now we're going to look at sine A cannot equal to 0. Okay? So if I look at sine, where sine cannot equal to 0, that's going to be both here and here. So in this case, it is just going to be A cannot equal to n pi. Okay? And all of these is n is an element of integers. N is an element of integers, and n belongs to integers. Now, if I combine these together, all of these ones here are in this one as well. Okay? This is kind of a subset of that. So my answer is now A cannot equal to n pi and pi over 2 plus n pi. And that's when n is an element of integers, or n belongs to integers. So these are all of my answers for these here. So for C, it wants us to show the non-permissible values on the graph of each side of the identity. So on my left side here, we have quite a few different types of non-permissible values. We have points of discontinuity and vertical asymptotes. So in this case here, my vertical asymptotes are every time, if we're looking at this, is going to be at every time we have pi over 2, because it's every time cos is on the bottom, pi over 2 plus n pi. So I look at that here. We have, this is negative pi over 2. This here is going to be negative 3 pi over 2, pi over 2, and 3 pi over 2. So these are going to be my vertical asymptotes. Okay? Now, if I look at this, we have point of discontinuity. But in this case here, we have 1 over cos A, and which are all my n pi's, and then here we have pi n. So it's only half of these are going to be used, and those are only going to be my negative halves. So then my point of discontinuity for this one here is only going to be at these second points here. So we have one there, and not the even. So the 2 pi's and the 0 won't have it in this one here. So this one's going to look like this. Okay. Now, if I look at the cotangent one, we have the same thing, because 1 over cotangent, so we have all of my signs here, so we're same thing again, same points of, or my equations, my asymptotes are at the same points. But now my points of discontinuity are all over, because if we look back up here, it's every pi over 2 is the cos, because we have 1 over cos as well. Where this one, it's only 1 plus cos A, so my points of discontinuity are only on the, if we go back here, are only going to be on the odds. Because of this equation here, it's only every odd one. But on this side here, we're looking at every cosine possible, and every sine is going to be my point of discontinuity on this one here. So for this case here, my point of discontinuity is every sine. So we have there, 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 and there. So my graph for this one's going to look like this. Okay. Now, on my last question here, it says prove this following identity. So we want to prove this one. So I'm going to start with this side here, which is the more complicated side. So we have secant squared of x all over secant squared x minus 1. Well, secant squared x minus 1 is the same as, if we subtract 1, tan x squared. So this is going to be, so I'm only looking at the left-hand side here. Okay. Now, what is each of these? This is going to be equal to. Okay, putting in sine and cosine. Okay. Now we have division of a fraction, so this is going to be the same as 1 over cos squared x multiplied by cos squared x all over sine squared x. These will cancel off, and I'm left with 1 over sine squared x, which is the same thing as cosecant squared x. And it is the same, so we just proved it.